Good afternoon, everybody. Let's get started with the class or announcements. So homework 8 is due this Wednesday. I'll have some guidance on that today. We'll do an example problem right at the start of class. If you haven't responded to the FCQs, I would appreciate some feedback on the course. So you should have gotten an email with a link to review the course and fill out that FCQ so I could get some feedback. And if you have any questions that you'd like to talk about during office hours, just stop by right after class and I will answer them right after class at office hours. Okay, so we left off last time talking about lighting up LEDs with logic gates, and I wanted to add a microcontroller into the mix because you have a homework problem that looks something like this that involves a microcontroller. Okay, so here's an example problem with microcontroller and logic gates. And the problem is this. So you have these LED states. LED 1 is on, LED 2 is off, LED 3 is off, and the load is powered. Okay, so this LED is on. I'll write on here. LED 2 is off, and LED 3 is off. Okay, and the load is powered, which means there's current flowing through the load. So the question asks, what is the value of the byte formed by bits 0 through bit 7? Okay, and express the answer in hexadecimal. Okay, so we have to figure out what are these output ports of the microcontroller set to, and then we can fill in this digital word, this byte down here, based on bit 0 through bit 7. Bit 0 is called the least significant bit. Bit 7 is the most significant bit. So that's the order of the bits in this byte. Okay, so we have LED 1 on. Let's figure out how to turn this LED on. We have 5 volts on the right side of this resistor in series with the LED. So in order to get plus minus 5 volts across that LED and resistor, we need a logic level 0, or actually 0 voltage right here. That will put 5 volts across that LED. So this gate is a NAND gate. And the only way to get a 0 out of a NAND gate is to have 2 1s at the 2 inputs. Okay. If this were an AND gate and you put 2 1s, you'd have a 1 at the output, but the NAND gate has this inverter bubble on the outside on the output. So you need 2 1s. So that means bit 7 is a 1 and bit 6 is a 1. LED 2 is off, so you want 0 volts across this resistor and LED in series. So to get 0 volts there, when the cathode of the LED is connected to 0 volts, you need 0 volts or 0 at the input here to that series combination, which means B5 has to be an output of 0. Okay. Then this load is powered. Okay, so there's collector current flowing through this transistor, which means there must be base current flowing through that transistor. And to have base current flowing through that transistor in order to saturate it, we're going to need a non-zero voltage at C. So that has to be a logic level 1. And if this is 5 volt logic, that's going to be 5 volts. So we assume that resistor was designed so that this transistor saturates when 5 volts is applied. Okay, this logic block is a logical multiply. So there's no logic gate drawn here, but since this is a logical multiply, we know it's an AND gate. An AND gate is a logical multiply, but For some reason, we express this as a multiplier, not a AND gate. Okay, so to have a 1 at the output of an AND gate, you need 1s at the inputs. Okay, so that's bit 4 and bit 3. So bit 4 is a 1, bit 3 is a 1. Okay, that takes care of all but 3 bits in this byte. And now we have LED 3 finally. LED 3 is off. There's 0 volts on the right of this diode in series with a resistor. We want 0 volts across that resistor and LED. So that means we need a logic level 0 here at the output of that OR gate. The only way to have a 0 at the output of that OR gate is to have 2 zeros at the input. Okay, so that means B0 is a 0. And the output of this other OR gate has to be a 0. And the only way to get that is to have those inputs to that OR gate equal to 0. All right, so this is like a 3-input OR gate, actually, made of two input OR gates. Okay, so we have zeros here. Okay, so here's our binary word. This is base 2, 1101, 1000. That's binary base 2. And so then to express this value in hex, you start at the radix and imagine it here. There's no radix point shown, but it's going to be all the way on the right if this is just an integer value. So we have 1000. That is an 8 base 10, which is also an 8 base 16. Okay. And then we have 1101. We're going to convert this to a hex value. So that is what 4 or 8 plus 4, which is 12, plus 1 is 13, base 10, which is a D as in delta, base 16. Okay, so the answer is D8, base 16. That is the value in hexadecimal to which you would set this byte in order to have LED 1 on, LED 2 off, LED 3 off, and the load powered. Okay, so that should help you out with your homework problem that you have due this week. All right. Okay, so next I wanted to switch topics. We have hit another milestone in the course. For the rest of the course, rest of this week, we're going to talk about DC motors, probably finish that up either today or early on Wednesday, and then we're going to start some final exam review on Wednesday. So let's talk about DC motors. Okay, so let's start with some vocabulary. And you may know this, but I want to make sure we're using the same terms here when I'm describing an electric motor. So we're talking about electric motors, which are made of, well, a part that stays stationary. We're going to call that the stator. And the part that rotates is called the rotor, and that has some subparts within it. And that rotor rotates on a shaft that rotates on bearings of the stator. So the basic principle behind what makes an electric motor turn is this. This is actually described as a DC linear machine. Okay, it's a way to apply a force on an object linearly with an electric current. Okay, so imagine this. Imagine you have a battery and maybe a resistor and a switch, and then you have 2 rails. Okay, so these rails are conducting. They can conduct. And then you put a conducting bar across those rails like this, such that it could slide left and right in this figure. Then apply a magnetic field. So here's a magnetic field. These X's represent a magnetic field going into the slide, into your screen. Okay, that's what the X means here. And the bar is within that magnetic field. So if you close the switch, you're going to cause current to flow out of the battery through the resistor, through the switch, down through this sliding bar back to the battery. So that's going to be the direction of positive current flow. That's what IA describes here. If you do that, there's going to be a force on this bar that is described by IL cross B, where I is the current, L is the length of that bar, and B is the magnetic field. Okay, so IL cross B, if you look at the directions here, if I is a positive current and B is into the page, you use the right hand rule and you would see that the bar would slide to the right. There would be some force on this bar that would slide to the right. Okay. Now, so this is a DC linear machine. Often we use this concept to implement a DC motor. So this is how you turn that DC linear machine into a DC motor that rotates. So imagine this. Imagine you have a loop of wire. So here's a single loop of wire. And it's in a magnetic field. So you have North Pole over here, South Pole over here of permanent magnets that are separated by some gap between which you have this coil of wire. Now that coil of wire is connected to two commutator halves, I'll call them. So this circular object right here, that's a commutator. Notice there's a split in the middle, so there's no, there wouldn't be any conduction of current from, in this case, the left half to the right half. But if you take the commutator and you apply brushes, so these brushes actually slide along the outer perimeter of this commutator. This can rotate. The brushes stay stationary. The commutator rotates. And then you apply some current through a couple wires. So current would be conducted like this, up through one of the brushes to half of the commutator, through that loop of wire to the other half of the commutator, to the brush, and back down to the source of that current. So if you do this, then what you're going to see, if you remember the IL cross B direction from the last slide, you're going to see a force on the upper left here, up, and as the current flows, you're going to see a force down on the lower right, and that will cause this loop to rotate. Okay, so that loop is free to rotate, and then when this commutator spins 180 degrees, you're going to have the same thing, except one side of the loop goes to the other side, but the current on the lower right is always flowing in that direction. The current in the upper left is always flowing in that direction. Now here you might say, well, wait a minute, what happens when this commutator spins 90 degrees? It looks like that's going to short out from one brush to another, and yeah, it would. So practically you don't have generally two sections of commutator, you have more. And so a more realistic view would be something like this. So here are the commutator bars, okay, and here are the brushes that would be maybe spring loaded up against that commutator bar, or the commutator touching one or two of the bars, each brush. And then you would have coils of wire around this armature here, okay? So you'd have a wire maybe coming from this top commutator bar up and around several times and down to the bottom commutator bar, and then take pairs of these bars and attach wires, coils in these slots on the rotor. Okay, so that's a more realistic view of what a rotor of a DC electric motor might look like. Okay, so replace that 2-bar commutator with this, and then you have a more realistic motor. So here's another view of a two-pole DC motor. So inside here, this is like a cross section looking along the shaft of the rotor. Here you can see the coils represented by these circles. Current would be going in from the commutator bars on the right. Current would be coming out on the left. And in this case, this motor is showing a magnetic field not created by permanent magnets, but by field windings. So you can use permanent magnets, but you can also use a coil of wire on the stator to create the magnetic field. So here in this case, you'd have, look at the top, you'd have current going in at the top right here, and then out at the bottom right. And so there's, imagine a coil of wire running front to back and along these slots here, creating that magnetic field. On the left side, you have the same thing, current going in at the top, out at the bottom. Okay, with the way these coils are oriented, you'd have a south pole on the left, north pole on the right, just like you'd have with permanent magnets, and then you would have an electric motor here. Okay. Now there are different types of electric motors, and motors are often chosen based on what power is available. Is it AC power or is it DC power? What kind of torque characteristics and maybe even speed characteristics do you need out of the motor? And then what mechanical components do you have available? Gears, pulleys, etc. So these four plots show torque versus speed. Okay, so if you look at the lower left here, this is a common DC permanent magnet motor. Right? One of these small motors you can use in lab. You'll often see these in lab. And this is a torque versus speed plot. So speed is in RPM. Okay, so think RPM when you think speed. So the way this works is that if you were to let the motor free run and not apply any external torque, that would be as fast as you could get that motor to turn. That would be the no load speed. You're applying zero external torque to that shaft. You know, it has some friction inside, there's some internal torque, but I'm talking about external torque applied to the shaft. So that's letting the motor free run. If you apply torque, then what's going to happen is the speed is going to get lower. So RPM is going to fall as you increase torque along this line. And finally, you're going to get to the point where you apply so much torque that the RPM falls to zero, and that's called the stall torque. So that's a common DC motor. That's the characteristic of it. With these motors, you apply a DC voltage, whatever the rating is typically, and the motor spins. And you can gear that motor down. You can use that motor just as a either a motor that's controlled by. We'll talk about controlling speed, but you can control the speed with pulse width modulation and control direction with an H bridge, and we'll talk about that. Another kind of motor that you're likely to run into is a stepper motor. So a stepper motor is a synchronous motor. And this has an interesting torque versus speed characteristic. The speed is independent of load as long as you're within the rated load limit of the motor. Okay, so as you apply more torque, the speed is the same up until, well, the motor might stop or start skipping steps. So we'll talk about stepper motors as well as DC motors. Okay, so let's talk about speed control of a common DC motor. So if you want a motor to run full speed, you can just apply, let's say 5 volts to a 5-volt motor and that motor will run. But you could also vary the speed of that motor using pulse width modulation, just like in lab when you controlled the brightness of an LED. So you're going to pulse the motor with varying pulse widths to control average power delivered to the DC motor. And you did this in lab with an LED where you controlled the duty cycle of a signal generator, a function generator, in order to control the brightness of an LED, except now you can control the speed of a motor. So the duty cycle is the time that the power is on applied to the motor over a cycle divided by the cycle period. So 100% duty cycle is when you apply the rated voltage and the motor spins at 100% its speed for a given load. If you want to slow that motor down, then you you can apply, for example, an 80% duty cycle where the voltage is high 80% of the time, and 20% of the time the voltage is low. Okay. If you want to really slow the motor down, you can drop the duty cycle. Here's a 20% duty cycle. So power is applied to the motor 20% of the time over the period of that square wave. And typically, you have a constant frequency but different pulse widths. So the pulse width is changing here, but not the frequency, not the period of that square wave. And you say, well, wait a minute, doesn't this looks like the motor is on, the motor turns off for a little bit, the motor's on, the motor turns off for a little bit. So wouldn't that be weird? Well, this is on the scale of milliseconds, not seconds. So yes, if this were on the scale of many seconds along this axis, the motor would turn on and off. But the motor is actually acting like a low-pass filter, which causes an averaging effect. So the inertia of the shaft and the load is going to essentially low-pass filter and cause this to be the motor to run at a constant speed, but lower than, let's say, 100% duty cycle. If you want to stop the motor, apply 0% duty cycle, 0 volts, and the motor stops. So that's a way you can control speed of a DC motor. How about direction? What if you want to reverse directions? That's where you would use a circuit called an H-bridge. So this is an H-bridge. It's an H-bridge because it kind of looks like an H here. Imagine you have 5 volts applied from a power supply to this top node, and you have the bottom node grounded. In the center is this motor, and let's define what direction of current causes the forward direction spinning of the motor. Okay, so let's say when you have positive current flow from left to right, we're going to say the motor spins in the forward direction. If you reverse the current through this DC motor, then you get the shaft spinning in the opposite direction. So right to left, let's call that the reverse direction current. So we have to figure out some way to have current flow left to right and then switch right to left when we want to go in reverse. Okay, so with these switches, you can cause current to go in the forward direction by closing switches A and D. That'll cause current to go down from the source, down through switch A, left to right through the motor, down through switch D, down to ground, and again, back up to the node because there's some imagined DC source in here. You can create a table that shows the switch states and the direction of the motor shaft. Okay, let's suppose you want the motor to spin the opposite direction. Well, then close switches C and B. Okay, then current would flow down through, down from the source, down through switch C, through the motor in the opposite direction, down through B, down to ground, again, back up to the top node through the source. You can add that to the table. So these are the switch states to cause that H bridge to make the motor spin in the reverse direction. Okay, so you can control the direction with this H bridge, or you can stop the motor. Just open up, if you open up switch C right here, or open up switch B and C, the motor will stop. Okay, so you can implement these. Typically, you don't implement this with mechanical switches. You would use transistors for A, B, C, and D. Typically, you would use NPN transistors here at the bottom for B and D, and then PNP, we haven't talked about those, but up at the top. So you could reference your transistor circuit to 5 volts instead of ground. But just know that you could swap out these switches for transistors, and now you could have a microcontroller control the direction of the motor. And note that you could also use this H bridge to not only change directions, but opening and closing these switches using a microcontroller would let you pulse width modulate the power applied to the motor. So you can control direction with the H bridge, and then you could also control the duty cycle of those switch closings to control speed. So forward, backward, full speed, stop, and any speed in between. There are integrated circuits that are designed to do this, to act as H-bridges for electric motors. Here's an example. Here is an example application schematic controlling this motor using this chip. Okay, so here's the motor. Forget about those diodes for a little bit. I'll explain what those are. But the output of these buffers, remember we talked about what a buffer is. A buffer has the output equal to the input. What good is that? Well, these buffers are actually current drivers. In other words, the input is a low current control signal, and the output controls current either into or out of that buffer at a higher level than your logic signal could provide. Right? That is the input to those buffers. So imagine the outputs could source or sink current at a high enough current level to drive that motor, to make that motor spin. Okay, so if you have, let's say, pin 3 high and pin 6 low, you would have current going from pin 3 to pin 6, and that motor would spin in one direction, and then you could reverse the direction by having pin 6 high, pin 3 low, the current will go in the opposite direction. Okay, and you control those, the output pin 6 and pin 3 with the inputs pin 7 and pin 2. So here you can see the truth table. If you hold the enable pin high, then this is how you would control the motors: turn left, turn right, and stop the motor. Okay, these diodes. So these diodes are important. Remember we talked about the voltage across an inductor. Voltage is equal to L di dt. Motors have coils in them. Coils have inductance. And so what happens is if you try to shut the current off through a motor very rapidly, you get a big spike of voltage. Di dt is large. And what these diodes do is they conduct current when that spike happens, and they dissipate that power. They absorb that power. Okay, and these diodes look like they're doing nothing normally because you have, let's say VCC2 is some high voltage, and then this node here is some load voltage. That diode and that diode would be reverse biased if either one of these are low. If either one of these are a high voltage, then you can't have current flowing from backwards through those diodes from cathode to anode. So it looks like those diodes are doing nothing. So these diodes only do something when this voltage exceeds VCC2. It tries to go to a very high voltage in a spike, and then that diode conducts and dissipates the energy that was stored in the inductor. Or if this voltage tries to go negative, either one of these terminals tries to go negative, then current conducts up from ground, and the energy of the inductor is dissipated in those diodes. Okay. So you can build an H-bridge out of transistors, MOSFETs, BJTs, or you can use these dedicated integrated circuits as motor controllers. And again, you could use these control inputs 1A and 2A to pulse width modulate that motor as well as controlling speed. Right, so that should get you going with DC motors and DC motor control with H-bridges. Let's talk about a different kind of motor. Let's talk about stepper motors and why you would use stepper motors. Right? So DC motors, you apply power, they spin, you can control them with H-bridges and pulse width modulation. Stepper motors are different. They're controlled differently. And they're generally used for more precise control of a shaft. So you can perform precision speed control with stepper motors, or you can even perform precise rotor angle control. And if you attach the rotor to a gear or to a pulley and then attach it to a chain or a belt, then you can control a linear position with a stepper motor. Okay. So why would you want to use these? Here are some applications. So many devices that have some kind of head or like a print head in a inkjet printer, right? Uses a stepper motor that's attached to either a belt or some kind of gear drive to move the head of the printer. So you want a precise, you want to know the location of the print head and be able to control the location of the print head in a printer. So you use a stepper motor. Um, in robotics, where you have to point something in a particular direction or move a shaft or a wheel a precise amount, you could use a stepper motor. 3D printers use stepper motors typically, and also CNC machines can use stepper motors. Okay. And someone asks, will this be on the exam? Yes, this will be on the exam. So these concepts are important. So you'll see some examples in the review. Okay. So how do you control stepper motors? Let's talk about how they work so we can talk about how they are controlled. So imagine you have a cross section that looks like this. So this is the stator, stay still, and this is the rotor, this spins. Now, imagine you have coils that are wrapped around these, I'll call them tabs as they're drawn here, where you have a coil wrapped around A and it goes behind the motor and then it wraps around A prime. So you could create a magnetic field between A and A prime. Imagine the same thing for B. You could create a magnetic field with a coil of wire wrapped here and wrapped here to create a magnetic field between B and B prime. And then between C and C prime and D prime, you could independently create magnetic fields. So the way this works out is that if you energize A and A prime, this rotor is going to tend to want to stay where it is. It wants to minimize the gap where this magnetic field is created between A and 1 and 4 and A prime. That's where it's going to stay. If you energize next B and B prime, creating a magnetic field between B and B prime, this rotor is going to rotate so 2 aligns with B and 5 aligns with B prime. So I've turned one step to the right. And then using your imagination, you can imagine 3 would be somewhere around here. You energize C, de-energize B, energize C, and then 3 would align with C, and 6 would align with C prime. And so that's how you could spin this rotor. You energize A, B, C, D, A, B, C, D, and the rotor will step such that 1 aligns with A, 2 aligns with B, 3 aligns with C, etc. You can imagine this being controlled with some kind of mechanical switch. It's not a mechanical switch, but let's just use this as an example. So if I want to energize coil A, I could have this DC source with a switch connected to A. And then I could switch that switch to connect to B. That would energize coil B. I could switch it to C. I could switch it to D. So I'm energizing one coil at a time. And so if I want to spin this motor clockwise, the rotor clockwise, I would energize A, B, C, D, A, B, C, D by moving the switch through those positions. If I want to spin in the opposite direction, counterclockwise, I would energize D, C, B, A, D, C, B, A in that order. Okay, if I want to control the speed of this motor, that's the rate at which I energize those coils. Right? If I energize A, B, C, D, or I speed it up, A, B, C, D, the motor will spin faster if I speed up that switching. So it would look something like this. As you energize each one of these sets of coils, pairs of coils, the rotor will spin to align those tabs with the corresponding coils. If you want to spin in the opposite direction, energize in the opposite order. Okay. So in real life, a stepper motor looks like this. This is a common 5-volt simple small stepper motor. Here is a diagram out of the data sheet. And so this motor uses in the circuit a 5-volt common. So you can see the 4 coils in here that can be energized. And 5 volts node voltage is applied to red and green. And if I want to energize this upper left coil, I would ground the yellow. If I want to energize the lower left coil, I would ground the orange, right, wire. If I want to energize this coil upper right, I would ground the brown. If I want to energize this lower right coil, I would ground the black. Since 5 volts is common, I'm grounding the wires, the coils that I want to energize. I'm doing that here with transistors Q1 through Q4. So these transistors you could control with a microcontroller, have an output port of a microcontroller connected to a resistor, connected to the base of each one of these transistors. Right? So that would let me have 4 bits of a microcontroller's output ports control the speed and the direction of this motor. And you can see the order here. If I want to have counterclockwise rotation, step 1, 2, 3, 4, here is the order of energizing those coils, or the states of the transistors. So on means saturated, off means cutoff. If I want to spin the opposite direction, energize in the opposite direction. Okay, if I want to control the speed, control how fast you switch between steps. Okay, so this stepper motor doesn't have just 2 wires where you power it. There are actually 6 wires coming out of the stepper motor that give you access to these windings. And you need to provide external control of current through the windings to control the position and speed of the rotor. Okay, so it's a little more complicated than a DC motor, but it gives you a different type of control for precision, speed, and angle control. All right, here's a stepper motor out of another data sheet. So you can see the windings, and you can see the wires and the colors and the names of those wires. And here's an example of a table that describes how you implement clockwise and counterclockwise rotation. In this case, red is common. Apply, if this is a 5-volt motor, plus 5 volts, and then ground the corresponding wires in this order where the minuses are shown in those cells. And there are interface circuits available to control stepper motors with microcontroller outputs. And typically, there's something like, you can use a chip like this that has logic level inputs, and the outputs here are open collector outputs to ground. So you could ground the wires that you need to based on the microcontroller ports that are applied to the inputs here. Okay, so you can use transistor arrays, you can use H-bridge ICs actually to control the stepper motor coils, and specific motor drivers are available that can be used for this. All right, here's another stepper motor, another table, just showing you that there's some commonalities here. So 6 wires, here are the phases. Here's the common. The common is plus 5 volts here, ground the appropriate phase of wires to spin the motor. This motor actually has, let's see, I wanted to point this out because this motor has 20 steps per revolution. So there's 18 degrees of resolution per full step. So that's part of a specification of a stepper motor typically. Okay. And so typically stepper motors require more current per phase, per coil, than a microcontroller could provide out of its digital port. Okay, so, and if you try to drive a motor directly with digital ports, believe me, I've tried it, you will likely cause unpredictable behavior of the motor. You typically need not only higher current capability to drive these phases, but also some isolation between the digital circuit output and the stepper motor power. Right? So we talked about DC motors, we talked about stepper motors, and there's another kind of motor you're likely to run into, and that's called a servo motor. Okay, so servo motors are also used to control angle and linear motion, but they operate in a different way compared to stepper motors. You'll see small servo motors on RC vehicles, radio controlled vehicles, radio controlled aircraft. You also see large servo motors in industrial applications. Okay, so they span a wide range of torque. But servo motors are typically designed around this type of operation. So inside the servo motor, and here's an example of a small servo motor. Inside the servo motor, you have these blocks. And what these blocks do is they allow the motor to use feedback to achieve a desired result. That desired result is either position or a speed. And a servo motor typically controls position of the shaft. Okay. This feedback is similar to the negative feedback that we talked about for op amps. For op amps, negative feedback drove the input differential voltage to 0. You could consider that input differential voltage to be an error voltage. A servo motor drives the error to 0, where error is the difference between a commanded position and an actual position. And you set the commanded position or the desired position using a control signal. And then negative feedback, just like an op amp, minimizes the difference, tries to drive it to 0 between the actual position and the commanded position. Okay. And so basically, here's how it works. You have a DC motor, and so this DC motor, when its shaft spins, it spins through these gears, which reduce the number of turns. This is a reduction gear down to an output shaft. This potentiometer is connected directly to that output shaft. And so that output shaft only spins a finite amount of angle. It doesn't continuously turn. There are servo motors that can do continuous turns, but typically this would be maybe 180 degrees a turn, maybe 270, maybe 90. Okay, that's the range of the angle of that shaft. So when the potentiometer is connected to that shaft, you could configure it in a voltage divider so that a voltage corresponds to an angle of that shaft, right? Remember that as you turned the shaft of the potentiometer in your project, right? In your project, one of your labs, and we talked about this in class, you could have an output voltage that corresponds to the position of the shaft of the potentiometer. So you can use that potentiometer as a position sensor, as a shaft position sensor. So that's what this voltage is here. It tells the motor controller what the position is of that output shaft. So this control signal that we'll talk about, that is input to this motor controller and to the motor. Or power is input into the motor controller and to the motor, and then there's a ground. So that control signal defines a desired position, a commanded position. The motor controller has that position. It also has the actual shaft position, and then it can turn that motor in a direction to minimize the error or to drive that error to 0 between the commanded position and the actual position. And that actual position is sensed by the potentiometer. So if you break one of these motors open, one of these small servo motors, you would see this. So this is the motor controller right here, this circuit board. You can see there's an integrated circuit right there with some supporting electronics. You can see the DC motor is here. Okay, so here are the two power connections to the DC motor. Here are the gears. You can see the gears connected to that shaft, and the shaft has, that kind of bracket on it. Okay. And here's the potentiometer. This is the back side of the potentiometer. You can see the 3 pins. Here are the 3 wires coming back down to the motor controller. Okay. So that's looking at the inside of a servo motor. Let's talk about this control signal. So for simple, small servo motors, this is pretty common. If you create a square wave or a pulse that has a constant frequency, but you vary the pulse width, that is the control signal for the input of a small servo motor. So typically, these servo motors turn a range of 90 degrees or 180 degrees. You'll find different ranges. And again, there are some that are continuous turn, but let's not talk about those right now. And you're essentially using pulse width modulation to control the angle of the servo shaft, right? So you have a constant frequency, but you're varying the width of that pulse. And the typical period for these servo motors is 20 milliseconds, which is a frequency of 50 hertz for that square wave. And the typical duration range is 1 millisecond to 2 milliseconds, and that controls the angle over a full range. So you can use a microcontroller and microcontroller timers, timer peripherals to produce this control signal. And then in software, you can command the servo to spin to different angles. Okay, so those are 3 types of motors that I think you're likely to run into if you get into projects that use motors. There's many different types of motors out there: AC motors, induction motors, brushless motors, but this is just an intro to that. Okay, so some key points about servo motors. Servo motors use a control signal and negative feedback to position a motor shaft. And just for comparison, if you compare servo motors to DC motors, servo motors used a pulsed voltage to control position, right? That's pulse width modulation to achieve a specific angle. We also used PWM for DC motors, but DC motors can use a pulsed voltage to control speed. Instead of position, you're controlling speed for a DC motor. That's PWM to achieve a specific speed. And both servo motors and stepper motors can be used to control the position of a shaft. And so if you compare stepper motors to servo motors, a servo motor shaft angle is controlled using closed loop control with negative feedback. That control loop is trying to minimize the error between a commanded position and the actual position. Whereas a stepper motor is achieving a shaft angle by energizing phases or coils within the motor. All right, it's a different type of control to achieve a similar result where you're controlling an angle. Okay, and so I think you'll see some example problems. We're going to do some final exam review, so you'll see some example problems where we talk about H bridges, we talk about stepper motor control. And that'll give you some idea of the kind of questions that could be asked about these. But mostly I wanted to get across the fundamental concepts so that when you run into these types of motors, you'll understand how they work and how to control them. All right. Okay, so just about right on time here. In closing, don't forget homework 8 is due Wednesday. That's the last homework of the semester. Our last lecture will be on Wednesday. We will do a final exam review. If you have a chance, please fill out those FCQs, click on the link that you got in your email. I will start office hours right after this class. So if you'd like to talk, just stick around. If not, I'll see you next time. Have a great night.